Hello guys, in this video we're going to talk about diesel engines, about combustion in diesel engines particularly, and we will take an example, the Duramax 6.6 liter by General Motors, which is used for trucks and pickups, different models of this corporation. Um, the engine is quite interesting. Uh, Here is picture. So it is 90 degrees V8 engine with variable geometry turbocharger and common rail high pressure fuel injection system. It was introduced in 2001, the first modification LB7, and since then it had 6 or 7 generations. There is an interesting site which the link to this site I will add under the video, so which tells the history of all generations of this engine. It had initially compression ratio 17.5 to 1, and a little bit unusual bore to stroke ratio. As you can see, bore is greater than stroke. And initially it had the fixed geometry turbine by Ishikawa-Dima, and but the next generation LI already had the variable geometry turbocharger by Gerrit, and then the compression ratio was dropped to 16.10 to 1, and the latest modifications L5P have compression ratio 16.0 to 1, and they switched from Bosch to denser fuel injection system supplier. So we will focus on the model LML, which was in production, in manufacturing from 2011 to 2016, and this engine has compression ratio 16.8 to 1, and the variable geometry turbocharger and Bosch high pressure common rail direct injection system, which enables up to 30,000 psi pressure in the rail. So converting to bars, it is about 2,000 bars or 200 megapascals. So let's open Blitz-PRO first. Log into it. I made some initial setup of the engine. As you can see, its bore is greater than stroke, so it's more common for gasoline engines than for diesel engines. And the compression ratio 16.8 to 1, number of cylinders 8, and so on. So I made all this setup using the information from internet. So the valves, as you can see, it has the 4 valves per cylinder, 2 for intake and 2 for exhaust. So I found this geometry, but we will focus on the combustion process simulation. So the most important page for us is the fuel page, which is used for this setup. So Blitz-PRO gives to the user the ability to calculate combustion in diesel engines in two modes. It suggests Разлейцев or Weber combustion model. Weber combustion model is quite simple. It is very similar to the model for spark ignition engines, and Разлейцев combustion model is more sophisticated, more complex. So we will discuss this model in this video to understand how it actually works. So also Blitz-PRO enables the calculation for single, double, and triple injection per site. And let's make our first calculation for single injection, and then we will try to understand why we use double and triple injection. We can open the tutorial also to make some setup to understand how it actually works. So we will open it on the page which refers to fuel properties and combustion. So okay, and now we can make the setup. So let's set the start of injection, well, about 2 degrees before top dead center, and the duration of injection about 12 degrees. So we will calculate the operation of the engine at the maximum torque, not at the maximum power mode, but at maximum torque. So the crank revolution is 1600 rpm, and the brake power is 173.8 kilowatts. So it is referred to this data. It is 765 pounds per foot. Yeah. So and for this operation we will make these calculations. Okay. Now we have set up the injection timing, yeah, and then we should set up the properties of fuel. We will use the regular diesel oil, so we won't change the setup of the fuel. And then fuel injection diagram. So this setup helps to calculate the law of fuel distribution during injection. The user can load some pattern of injection by himself, or use these functions to generate some injection curve. Altering these coefficients, we can alter the shape of injection curve. So let's do it. I don't know, like this. If we had some experimental data, we could match the injection pattern to experiment data. But if we don't, so we use some assumption. Yeah. And another important thing is how to choose and set up the injector to the engine. So generally it could be not so easy to find the information from manufacturer about the fuel injector they use on their engine. For example, for this particular engine, they have started um, at LB7 engine with the 6-hole injector and with the Bosch CP3 fuel injection system, which had the maximum pressure about 1,200 bars, and then they switched at LBZ modification to 7-hole fuel injector with higher pressure up to 1,800 bars, and then they have switched to the 8-hole injector at the LML modification with significantly higher injection pressure up to 2,000 bars. And the latest modification, as you can see, has even increased fuel injection pressure and new injectors. So yes, for LML modification, we know the number of injection holes, but we still don't know the uh, diameter of injection holes, and how to find it, or it could be possible. The situation is possible when we don't have neither number of injector holes nor their bores. So we can use from tutorial some advices which can help these to solve this task. So choosing the injector's nozzle joint. Yeah, we know the pressure which is uh, allowed to the fuel injection system, particularly for LML engine. It's 2000 bars at the rated speed, and generally it is a little bit smaller at the maximum torque, so we can assume it like 1,800 bars or 180 megapascals, and we can target this value uh, varying the duration of injection, the number of injection holes, and their bore to match some needed value of fuel injection pressure. For example, we can set the duration of injection 10, and for example, it could be 6 holes fuel injector. So we can check here the estimated fuel pressure in the common rail, and you can see it exceeds 3,500 bars. It's more than 350 megapascals, so it's very big. That's why we can increase the bore of these holes to match the needed um, fuel pressure, well, around 155 megapascals. But also we should look at the south diameter of the fuel droplets. So it just describes the average fuel droplets diameter during injection process. So it's very important in terms of optimization of fuel sprays and in terms of further combustion. We can use this table 2.4.1 in tutorial, which helps to target these values. The southern fuel droplets average diameter and the pressure in of injection, of fuel injection. So for common rail accumulator injection system, we can see that the pressure can be um, uh, varying from 120 to 300 megapascals at rated engine operation, and we should target the average diameter of fuel droplets from 10 to 16 micrometers. So we can see that using this combination we can match these. Um, but we know that LML engine has 8-hole fuel injection, and yeah, it has. So if we use 8 holes, we should make the bores smaller, just to keep the pressure on the needed level. And yeah, but as you can see, we get very small, uh, very small fuel droplets. So the other issue, we can just increase a little bit the duration of fuel injection, and then to drop down the uh, injector holes bore. So we get this combination. For example, I know which uh, which is the actual bore of injector holes for this particular engine. So we can set up this combination and then use for further calculations this injector. Um, all I know is just that it is the 8 holes injector. So once again, when we choose the fuel injector parameters, it is important to look at the estimated fuel injection pressure and at the estimated value of fuel droplets, which both have a great influence on the combustion process. Okay, so the next thing is to set up the fuel evaporation, and we can use also this guide from user tutorial, which talks about these coefficients we can take for this setup. I'm sorry. For example, here EC is 1.7 and AZ1. This value sets the time of evaporation of large droplets, so we can use different values, for example 10. And Y is very important parameter which helps to control the evaporation speed. Yeah, the greater is my, the faster is fuel evaporation. 3 is a constant from Lishevsky equations, and yeah, what's important is um, the length of the free flight of the fuel spray. So this picture shows an example. So the fuel injector sprays the fuel, and the fuel has the free flight until it just interacts with the walls of the piston or with the cylinder or cylinder head. So for this engine, we should find the design of the piston, and yeah, so let's see. Oh, as you can see, it has the ball and piston combustion chamber. So uh, it is about I don't know, maybe if the bore is 130 3 millimeters, so the combustion chamber diameter is about 60 to maybe 70 millimeters. So the length of the pre-flight, assuming that some interacting by the swirl, well, it's about 35 to 40 millimeters, maybe like this. So maybe 38 millimeters. So these coefficients describe and help to assume the drop of the operation speed after the fuel spray interacts with the walls of the cylinder. So we can use these as well as the parameters which describe the ignition delay. We use the Tolstov equation, and for the high-speed engine, we can use these recommended setup for constants Kn and B0. Okay, and then we choose relative combustion model, and we should set up all these coefficients using the table, which is a guide which helps to choose right parameters. For example, A0, A1, A2, B0, and all these parameters, they have some influence on the combustion process. We can use this picture, which helps to understand how fuel injection, fuel evaporation, and fuel combustion are connected together in relative combustion model, and then use it to set up the combustion. As you can see, this pattern shows the relative speed of fuel injection, and this one shows the fuel evaporation. As you can see, fuel evaporation rises, the speed of fuel evaporation, until it reaches, the sprays reach the walls of the cylinder. Then it drops, and then it rises again, and it drops until the whole fuel is evaporated. The speed of operation, the time of operation, is could be altered by applying the swirl ratio H and this multiplier My. And the drop in the speed of fuel operation due to interacting with cylinder walls could be set it up with key 0. Yeah, we made this setup before. And then we can see the speed of fuel combustion. And so many factors just help to control this pattern during the calculations. For example, A0 and B0, they help to set up the combustion of the fuel vapor which was occurred during the ignition delay, during this period, and as well as B0, Kn, and EA, the activation energy, helps to set up the duration of ignition delay. These values, CAC and PZO, they help to set up the process, this one, of the air usage during combustion. So from tutorial we can look this function which shows the usage of air in the mixture with the fuel vapor with reference to the relative duration of combustion for different types of combustion chamber, for different types of diesel engine. So we can use these coefficients from this table to make proper calculations. So this setup we will help to make the proper calculations, and if we will need some changes, we can just alter these values to get um, better results. Yeah, A1 and A2, they just are used to simulate the combustion at the fuel injection phase and some afterburning process. So the equations for Razleitsev model are also presented here, and we can use it by pressing the button equations. So okay, now let's try to make the calculation for this setup, and let's see what will we get. Okay, let's see what we've got. The calculation finished. Uh, let's see the report table, and yeah, we have the needed brake power, the good excess ratio, and the good brake specific fuel consumption value. But let's look at the maximum in-cylinder pressure. You see it's very big, it's 21 megapascals, it's too high. And let's also see some results of combustion simulation. So the maximum pressure raise is enormous, it's too big. Well, the engine works with some knocking, so it is dangerous for it. The average fuel injection pressure, as you can see, is 140 megapascals. Yeah, so we have some problems. Let's look at the diagrams. Let's look at the diagrams, indicated diagram and combustion diagram, particularly. So we can switch it to high resolution because we want um, to search, to investigate some things about the combustion processes. So as we can see that after fuel ignition, the combustion well occurs very fast, so the pressure rises very rapidly, and at the beginning we can see very fast rise of pressure in the cylinder, which causes this knocking. So it's dangerous for the engine, it produces noise, and this is not acceptable, as well as this high level of in-cylinder pressure. So, and let's look at the heat release diagrams. So this diagram shows the speed of combustion. As we can see at the beginning, it has a very rapid combustion, and then it slows down and continues. So why is it so? Let's look here. These complex diagrams will give us the answer. So uh, let's hide the values of integral data, and let's just analyze the speeds. So this blue line shows the speed of fuel injection, or the relative fuel injection. This green line shows the speed of fuel evaporation, and this red line shows the speed of fuel combustion. So as we can see, during the ignition delay, during this period, a lot of fuel was injected into the cylinder and evaporated already, yeah. And so when ignition occurs, all this fuel burns very rapidly, and this produces this rise in pressure in the cylinder at the beginning of combustion, this knocking, and also this produce this high level of the pressure in the cylinder. So how to deal with it? Well, and why it is so? It is so because the fuel is injected very fast. You can see only 12 degrees by crank angle. So and it is injected so fast because of high injection pressure. And also the droplets are very small because of high injection pressure, and that's why they evaporate very fast. Uh, these both makes the conditions for the fast combustion, fast kinetic combustion at the first stage of the fuel vapor which was made during the fuel ignition. And how to avoid this? Well, we can drop the fuel injection pressure, but this is not so good because it's not appropriate, because it makes the combustion last longer, and that's make engine less efficient. So how to deal with this? How they do it in common rail fuel injection systems? Uh, we can use double, triple, 4-time, 5-time, and 7-time fuel injection per one cycle. Well, Blitz-PRO currently supports only single, double, and triple injection. So what the idea? Let's see. We can switch to double injection, and we can inject some initial portion of fuel, small portion of fuel, just before the main combustion, and then the main combustion, the main portion of fuel. So this small pilot fuel injection will be, well, about, I don't know, maybe 8% of the total, from the total. Yes, it lasts about 1 crank angle degree, and the other fuel is injected at the main stage. So here we can see the fuel injection diagrams: pilot injection and main injection. So what is the idea? The idea is to inject the pilot a small portion of fuel which will burn before main injection occurs, and that will make the gases into the cylinder very hot. So when the main injection is the main fuel is introduced into the cylinder, the ignition delays is very small, becomes very small, and so we avoid this knocking combustion and this undesired first peak in the heat release diagram. Let's see how it works. We can also look here to match the pressures for the first and second stage. We can just adjust the share of the first pilot injection to make these pressures equal. Let's see. Well, I'll do a little bit like this. Yeah, it's very close because the rail is common, so it's obviously that the average pressure is similar to the pilot and main injection. Okay, so now we can make the calculation and we will compare the results with the previous one. So what is, once more, what would be the idea? The idea will be that as we can see, the temperature after combustion starting to rise, and there is the burned gases region and the fresh charged region. So the new fuel is just introduced. It will be introduced into the burned combustion zone, which has a very big temperature. So that's why the ignition delay drops significantly. So this is the idea. So let's see. Okay, the calculation is still in progress, and that will we hope that we will decrease the maximum pressure in cylinder together with the maximum pressure rate value. Okay, calculations are done. So let's look at the report table. And so what is the maximum pressure? As we can see, it's just become smaller, significantly smaller, and also the maximum pressurized rate is just dropped in 4 times. Well, much more smooth combustion. Let's take a let's have a look on the diagrams, indicated diagrams. And combustion diagrams. Okay, so let's switch to high resolution. All right, so as we can see, the first increase of pressure is due to pilot fuel injection, and when the second fuel injection starts, the temperature in the cylinder is much higher, so there is no such long ignition delay, and we have smooth combustion, so there is no such rapid pressure rise into the cylinder, as well as the maximum in cylinder pressure becomes a little bit smaller, significantly smaller. So here we can see the temperatures. Yes, this is the first injection. So the temperature in the burned region rise, and when this second portion is introduced, so we have very hot areas in the cylinder, so the ignition delay drops significantly. And let's have a look on the fuel combustion diagram, the speed of combustion. As we can see, this is the speed of the combustion of the pilot fuel injection, and then the second fuel, well, it is injected it is ignited very rapidly without so long ignition delay. And let's take a look here in these combined diagrams. Once again, I will hide the integral data and we will analyze only speed. So this is the first injection. The fuel evaporates and then combustion starts at this point. So the first portion of the fuel is burned, and then the second injection occurs. So the ignition delay for this second injection, as you can see, is very small. So there is no so much fuel vapor which occurs during this ignition delay, and combustion is very smooth and fast together. So we can compare it with this combustion diagram, when we, for single injection, when we had so long ignition delay and so rapid combustion at the first stage. We can also combine the diagrams for the single and double fuel injection. And as you can see, double fuel injection makes the pressure rise into the cylinder much smoother, and that helps to make engine operation much better. And also we can combine here the diagrams of combustion. It's interesting to see. Oh, that's it. So as we can see, the single injection, well, it just makes the combustion start very fast, so that produces this knocking, and while the double injection helps to keep combustion in control, under the control, and yeah, that makes engine operation much more smooth. Okay, so another option is just to we can also make our combustion process better, switching to the triple injection. So we can just split the main injection into two equal portions. Yeah. And it would be, let's see, we should just when we make multiple fuel injection, we should avoid interaction different injections one on another. Okay, so this one, so the pilot injection and two main injections. Okay, let's see the pressures. Okay, we can see that we can just adjust a little bit the pressures just to make them equal. Oh, they are almost equal. Okay, so let's see what we will get. Will we get using this triple injection? We can also just try to make first or pilot injection a little bit smaller. Let's try to make it smaller. Okay. I'll try to make the pressures equal. Okay, and here it would be oh yeah. Okay, okay, that's good. That looks good. Okay, so the pressures are almost equal. So let's see what will we have for this triple injection. And yeah, as we see, the progress of this engine was um, marked with continuous rise of the fuel injection pressure, and also uh, first injections were the solenoid injectors, which allowed up to 3 fuel injections per cycle, maybe 2, pilot and main. And starting the um, from the let me see, from the LMM, I think. No, starting from the LML, maybe. Yeah, from the LMA modification, which we try to calculate. Uh, they were used the piezoelectric fuel injectors, which are much faster than solenoid, so they allow to make up to 5 and even up to 6 fuel injections for one cycle, and that helps to make very precise control of combustion, and engineers can just match the pressurized curve to the desired region to avoid the very high pressures into the cylinder, to avoid excessive pressurized rate, and also to keep the engine efficiency, fuel consumption, and engine emissions in the desired range. Yeah. So, and the last generation uses denser G4S Gen 3 solenoid style injectors, so with different design, but they are also extremely fast, I think, to deal with this very high fuel injection pressure up to um, three up to 30,000 psi. So let's see. Let's see. Okay, the calculation is finished, and let's have a look on the results. So let's have a look on the report, and yeah, as we can see, the maximum pressure is only 18 megapascals, much slower, much lower than for single fuel injection, for example. And the maximum pressurized rate is only 1000 kilopascal per CUD, so we can say it's acceptable one. It's up to 3 and 3.5 times lower than for the single injection. We can see that injection pressures are in desired region, yeah? And the ignition delay is, as we can see, for the first injection is 3.6 CAD, and for the second and third it's about 1 CAD, so very fast. So let's have a look on the diagrams. Indicated and combustion diagrams. In high resolution to see the difference in these processes. So as we see now, the combustion process is very smooth. We can see all these 3 injections, first one, or not injections, or combustion, first pilot, yeah, first main, second main. So the combustion is really under control, and yeah, the pressure is significantly smaller than even for double injection. And let's have a look on the heat release diagram. We can see all these three injections pretty much under the control, so the heat is distributed very smoothly during the combustion period. So the combustion is very fast, but it's also not too fast in some regions, that makes the engine very efficient. And this combined diagram also is pretty interesting. So let's just wait. So we can see this triple injection, pilot injection, first main injection, second main injection, and it is obvious how we control the fuel evaporation and fuel combustion to make sure it takes very fast, but not too fast. Now, so we can combine this diagram for the uh, triple injection to the diagram double injection. Yeah. So here we can see how we control the maximum pressure by splitting the main injection to two portions, and by just um, making it more smooth. And when we add the diagram for single injection, as we can see, so yeah, the single injection, well, it has this stage of very fast, very rapid first stage combustion, and then the maximum pressure is 21.2 megapascals, while here is only 18 megapascals. So actually here the engine is cracked, while here it just operates normally. Yeah. And let's have a look on the combustion diagrams for double injection. Yeah, as we can see, splitting the injections for the triple injection. Let's just have only speeds. So we can just drop the heat release at the middle of the combustion process and just transfer it into a little bit further period. So and that helps to drop this maximum pressure. And when we compare it with the single fuel injection, yeah, we can really see this difference in combustion patterns. We can see this enormous first peak of combustion speed because of the fast combustion of evaporated fuel during ignition delay. So that's it. And it's obvious that we made some brief calculation, but actually we can play with these numbers and choose different shares for the pilot first main injection and post injection, or third main injection, and we can just adjust the fuel injection to the combustion process, and to get the desired combination of maximum pressure and maximum pressure rise rate, and of course the fuel consumption. So let's just compare the ignition triple ignition injection. Well, it provides the brake efficiencies 42.77%. Double injection makes 42.67, a little bit smaller, yeah, and the single injection makes it 42.83. So as we can see, this triple injection, for example, makes the engine operation um, almost equal efficient as the single injection, but of course the values of maximum pressure and the maximum pressurized rate are significantly smaller, 4 times smaller the pressurized rate, and up to 3 megapascals smaller the maximum pressure. So that's really important, and I hope you enjoy this. And if you have some questions, feel free to ask them about your different problems with calculations. So I'm always ready to answer them. See ya.